So, what exactly do we mean by application of integrals? When we write the integral from a to b of f of x dx from a to b f of x dx, this represents the net area between the curve y equals function of x and the x-axis. If f of x is greater than or equal to 0, meaning the curve lies above the x-axis, the contribution is positive. But if function of x is less than or equal to 0, meaning the curve lies below, the contribution is negative. That's why we call it an algebraic area. This is not just theory. Engineers compute road designs, economists calculate consumer surplus, and physicists measure displacement using exactly this principle. And all of this comes from that simple but powerful link: Riemann sums approximating areas and integrals giving us the exact value. Let's move into a formal definition. The area under a curve y equals f of x between x equals a and x equals b is given by a equals the integral from a to b of f of x dx. If the curve lies entirely above the x-axis, the area is automatically positive. If the curve lies below, then we must take the absolute value to represent the geometric area. And importantly, the function f defined from the interval a, b into the real numbers must be integrable. In practice, this means f should be continuous or at least piecewise continuous. That's how we ensure the integral makes sense. Now, let's classify the kinds of regions we may deal with. Case 1. A region bounded by a curve y equals function of x, the vertical lines x equals a and x equals b, and the x-axis. Case 2. A region bounded between two curves y equals f of x and y equals g of x over the interval. The general formula is a equals the integral from a to b of bracket f of x minus g of x bracket dx, that is, subtract the lower curve from the upper curve. This convention is very important, always upper minus lower, otherwise you risk negative areas that don't make geometric sense. Here's a very powerful shortcut: symmetry. If a function is even, that is, f of negative x equals f of x, then the area from minus a to a equals twice the area from 0 to a. For example, the parabola y equals x squared. If a function is odd, that is, f of negative x equals minus f of x, then the integral from minus a to a cancels out to 0. A classic example is the cubic y equals x cubed. So, by simply observing symmetry, we can save half the effort, or sometimes the entire effort of evaluating an integral. Let's connect all of this back to calculus. The Fundamental Theorem of Calculus states that if capital F of x is an antiderivative of small f of x, then the integral from a to b of small f of x dx equals capital F of b minus capital F of a. This means that instead of endlessly summing rectangles, we can compute the exact area by evaluating antiderivatives at the endpoints. It's like opening a shortcut tunnel between algebra and geometry. This bridge is what allows us to compute real geometric areas with exact formulas. Let's apply everything in a concrete example. We want the area bounded by the parabola y equals x squared and the straight line y equals 2x plus 3. Step 1. Find intersection points. Solve x squared equals 2x plus 3. Rearranging, we get x squared minus 2x minus 3 equals 0. Factorizing, x3 into x plus 1 equals 0. So, the intersections are at x equals minus 1 and x equals 3. Step 2. The area is given by the integral from minus 1 to 3 of bracket 2x plus 3 minus x squared bracket dx. Step 3. Integrate term by term. The integral of 2x is x squared. The integral of 3 is 3x. The integral of x squared is 1/3 x cubed. So, the expression becomes x squared plus 3x minus 1/3 x cubed. Step 4. Substitute bounds. At x equals 3, we get 9 plus 9 minus 9, which equals 9. At x equals minus 1, we get 1 minus 3 plus 1/3, which is negative 1 and 2/3. Subtracting gives us 10 and 2/3, or 32 divided by 3. To wrap up, definite integrals allow us to calculate areas of irregular shapes far beyond the reach of elementary geometry. In physics, this lets us compute displacement when velocity varies or work done when force is not constant. In statistics, probabilities are represented as areas under density curves. And in higher topics, we extend these techniques to volumes and surface areas of solids. So the humble definite integral is not just about abstract curves, it's a universal tool for accumulation, area, and measurement. And that concludes our introduction to the applications of integrals. In the next session, we will explore how to compute more complex regions and move towards finding volumes using integration. See you there.